Hello, welcome to our discussion of Hartree-Fock self-consistent field theory. In our last video we talked about an approximation method known as variation theory, which we use to compute properties of multi-electron systems. In this video we'll take it a little bit further and talk about how we use this variation theory to develop a method that is commonly used in computational chemistry. We'll start with just an introduction to a shorthand method of writing out integrals. There are lots of integrals that have to be used to do these computations, and so it's sometimes easier to write it in a shorthand notation referred to as bracket notation, and that's seen here. So for this simple integral involving the wave function psi star sub m and psi sub n, we can write this in terms of these brackets over here on the left side. We also sometimes write it just very simply with a. Of course, a represents the operator that's in this integral, with the subscript m and m, which is sometimes referred to as a matrix element, and we'll see why that's the case a little bit later on in the semester. Right, so the Hartree model. In this model, what we're going to do is we're going to take electron repulsion, and remember it was electron revulsion that prevented us from solving the Schrödinger equation exactly. And we're going to treat it as a smeared out charge so that we can talk about one electron interacting with a smeared out charge distribution from the other electrons in the atom or molecule. As noted earlier, this is a method that relies on the ideas associated with variation theory. And in this method we have, for a two-electron system, we would write an effective potential for electron 1 as according to this equation here, where the first term is a term which represents attraction between the electron and the nucleus. And the second term, which is in bracket notation, which remember, of course, is an integral, shows repulsion, where the electron 2 in this orbital, phi sub 2, where the electron 2 charge distribution is smeared out over the atom or molecule. And so we're calculating kind of this average smeared out charge distribution, and based on that, we're computing a repulsion associated with electron 1. And so that was, of course, with one electron. With multi-electrons, we can just very simply extend it so that we have a series of what we call one-electron equations, where the top equation here is the Schrödinger equation for one electron, where we have electron I, and we just use the term I here, but it could be electron 1, electron 2, whatever that might be, represented by orbital phi subscript I, and the epsilon sub I here is just the energy of that orbital. So this one electron Schrödinger equation allows us to calculate the orbital wave function and the energy the energy associated with that orbital. The V effective here then includes both, again, the attraction term on the left and the repulsion term on the right, but rather than having just one term, we have a summation here so that we've got a repulsion term associated with each of the other electrons in the system. So, for example, if we had 4 electrons in our system, then we'd have electron 1 interacting with electrons 2, 3, and 4. So in that particular case, we would have 3 terms representing those interactions with electrons 2, 3, and 4. Alright, so the self-consistent field method involves using an iteration of calculations until we have an asymptotic approach to a particular solution. We're looking for convergence on a particular solution. So let's say we start out with a guess set of wave functions. Let's say we have 5 orbitals. We might have 10 electrons. We have 5 orbitals. So we start with our 5 guess functions, which are our trial functions for each of these orbitals. And then what we do is we'll try to calculate an improved version of phi sub 1, where we're using the orbitals for 2, 3, 4, and 5 to calculate V effective. And then we are using the 1 electron equation, as noted before, to do that calculation. So we'll use that equation for orbital 1 and calculate an improved version for orbital 1 based on that. And then what we'll do is we're going to take that improved version of orbital 1, and we're going to take it, put it back in our database of orbitals. And we're going to use orbital 1, orbital 3, orbital 4, orbital 5 to calculate an improved version of orbital 2. So now we have an improved version of orbital 2 and an improved version of orbital 1. We'll take that version of orbital 2 and plug it back into our database. And then we'll do a calculation for orbital 3, where we'll use orbital 1, 2, 4, and 5 to calculate the smeared out charge distribution and the repulsion associated with it to get an improved version of orbital 3, which we then put back into our database, calculate an improved version of orbital 5, which we put back in our database to calculate an improved version of orbital 5. And then what we're going to do is start over. So now we have 5 improved versions for our orbitals. We have new versions of orbital 1, 2, 3, 4, and 5, which are better than what we started out with. So now we're going to go back and use those improved versions to calculate a better version of orbital 1, which we'll then use to calculate a better version of orbital 2, which we'll then use to calculate a better version of orbital 3, orbital 4, orbital 5, etc. So we have this cycle that, of course, can go on, but we continue that until we converge to some point, which is preset by the computational parameters. And when we get that convergence, then the computation will stop and give us a result for both the orbital and the corresponding, and the wave function and the corresponding energies. All right. So then again, of course, that was Hartree. What about Fock? Fock threw into the mix electron spin and applications of the Pauli principle. We know that our functions have to adhere to the Pauli principle for these electrons. So Fock's contribution was to add that to these equations. And so we get a total energy. Now, contrary to what you might believe, the total energy is not just a simple sum of the energies of the orbitals. So for example, this first term in this equation right here shows that we're summing over all the orbitals that we have in our system, and we're multiplying it by 2 because we have 2 electrons per orbital. So we're just taking the total sum of all the orbital energies and multiplying it by 2. But the thing is, that is not equal to the total energy, because that actually overcounts repulsion. If you think about it, the calculation of the energy for electron 1, for orbital 1, included repulsion with orbital 2. When we calculate orbital 2, we're including repulsion with orbital 1. So if we just add them together, you see we've actually included that repulsion twice in the calculation. So the simple sum of orbital energies does not give us the total energy. We have to correct that, and these last terms here correspond to the correction, and that is that we have a J term which we call a Coulomb integral, which, as we'll see, represents electron repulsion, and then we have a K term which corresponds to what we call an exchange integral. Right, so here are the Coulomb integrals and the exchange integrals, just showing you these. We're not going to do much in the way of computations in this class with these integrals. Just want to show you what they are. Again, the J term is a repulsion term, and you can see that that essentially shows us electron 2 represented by orbital J and electron 1 represented by orbital I, and that term itself is a measure of electron repulsion. The K term, on the other hand, shows orbital J with electrons 1 and 2, in orbital I with electrons 1 and 2. So essentially what we've done is we've swapped those electrons. That's why it's called an exchange integral. It actually has no classical counterpart. This does not correspond to any property that we speak about classically. It's a purely quantum mechanical effect that has a major impact on the energy of the system. And its presence is due to the conditions laid out by the Pauli principle, which we talked about in the last video. And so now we have questions about things like ionization energy. Koopman's theorem just simply says that the ionization energy is the negative of the energy of the occupied orbital. And of course we're talking about the lowest ionization, the first ionization energy here for an atom or a molecule. And you can think of it this way. We have energy levels with these orbital energies, and let's say E sub I here, epsilon sub I, or 1 is the highest occupied orbital. Then we have the ionization limit, which has an energy equal to 0, and so the energy necessary to remove the electron to get to the ionization limit is just very simply equal to negative the energy of that particular orbital. It is an approximation. We'll find out a little bit later on that it sometimes can get as close, but it's not the best way to determine ionization energies. All right, now let's talk about helium. As we noted earlier, that we're using in the Hartree-Fock method a smeared out charge distribution to calculate average repulsion, but that's not really sufficient. If you think about it, of course, there's instantaneous interaction between electrons. So if we have two electrons labeled here, 1 and 2, if one electron moves to the right, then the other electron, feeling that repulsion, is going to move to the right. And so as a result of that, this instantaneous interaction actually results in less repulsion than is the case if we just think of these average smeared out charge distributions. So the actual energy that we get from the Hartree that we measure in the laboratory is less than the energy that we can get from the Hartree-Fock calculations. And there is an absolute limit here. As long as we do not include this instantaneous interaction between electrons, we're always going to end up with an energy higher than the actual energy. And that is called the Hartree-Fock limit. So in helium, the Hartree-Fock limit corresponds to an energy of about negative 77.87 electron volts. If we compare that to the actual experimental energy, you can see that there's a difference here of 1.13 electron volts, which we refer to as a correlation energy. And this is as close as we can get with Hartree-Fock calculations. We cannot get any closer than this because we're not accounting for instantaneous interactions, and we're kind of stuck with these Hartree-Fock calculations. To get closer, we actually have to do away with the concept of orbitals altogether, and we can use other methods to do this. But the orbital picture of the atom and the molecule has to be discarded in order to get to closer energies closer to the actual experimental energy. All right, so just kind of reviewing here what the results are when we look at this. When we do the Hartree-Fock calculations with the orbital picture of the atom, we find that the energy depends on N and L, unlike the one electron system, which the energy only depends on N. And that the actual orbital energy depends on electron configuration. This is actually fairly important. Orbital energies are not static, and we'll talk about this in more detail in a few minutes. Okay, so here we have an orbital energy diagram that's typical of what might be found in your general chemistry textbook, that shows the energies of the 4s orbitals versus a 3d orbital as a function of atomic number. And of course what we note here is that at low atomic numbers the 3d orbital is lower in energy than the 4s orbital according to these calculations. When we get to potassium, however, we'll note that we have the situation where the 3d orbital is indeed higher in energy than the 4s. And so we write the electron configuration for this, taking that into account after we fill the 3-piece subshell with 6 electrons. the next electron, the 19th electron of potassium, will go into the 4s orbital, which we all learned from the Aufbau principle. And then, of course, if we move to, for example, scandium here, we'll note that in the case of scandium, which is atomic number 21, that the 3d orbital is lower in energy than the 4s orbital by the time we get there. We've learned from the Aufbau principle that the electron configuration of scandium has an argon core, of course, and is 4s2 3d1. Okay, that's basic rules that we learned. But if one looks at this diagram and takes it on face value, then one might assume, or one might naturally ask the question, why is it not 3d3? If the 3d electron is lower in energy, if the orbital is lower in energy than 4s, why don't all of these electrons, valence shell electrons, go into the 3d orbital? Well, again, the point here is that this diagram is very simplistic, and one has to be careful about its interpretation. The reality is that electron configurations are the determining factor when we are trying to determine the orbital energies. It's just not simply a matter of calculating these orbital energies and plotting them in this graph here. The specific energies depend very much on the electron configuration. So one has to be careful with these very simplistic interpretations. And this means that for scandium, this particular ordering of energies is such that this particular electron configuration that we see here, the 4s2 3d1, is lower in energy than any other electron configuration. All right. But that doesn't say anything about the ordering of the 4s orbital and the 3d orbital. For example, we may find in some atoms that the 4s orbital is lower in energy for one particular electron configuration, but then when we go to the ions, we might find that the 4s orbital is higher in energy. So it is, the ordering of these energies depends very, very much. I can't emphasize this enough. Please understand, ions and neutrals may have a very different ordering of orbital energies. We have to be careful about this. It's much more complex than we have been led to believe, as you know already from this P-Chem course, that things are always more complex than you were led to believe. And that's what makes it more fun, right? So if we just review this and go back, of course, to the Aufbau principle, which we all know and love, where the energy of the 4s orbital is less than the 3d orbital, we now know that that's not necessarily true, that in fact the orbital energies depend on the electron configuration, and that when we look at ions, for example, we'll note that their ordering of orbital energies may be very different from the neutrals. One has to be calculating those separately. So when we look at titanium 2+, which has 2 fewer electrons, of course, than the neutral titanium, the electron configuration is given here with 2 electrons in the 3d orbital and no electrons in the 4s orbital. So we often say that for these transition metal ions that the electrons are removed from the s orbital. That's a little bit simplistic as well. The reality is, what we're saying is that for the titanium 2+, the 3d2 electron configuration is lower in energy than the 4s2 electron configuration, or lower in energy than a 4s1 3d1 electron configuration. That's what we're saying. We don't want to just say that the ordering of orbitals is the same in all of these species. We just look at the overall electron configuration, and that's what helps us to determine what the energy is, and that again, the ordering of orbital energies is dependent on the specifics of the electron configuration. So, you know, in the cation case, we might have this situation where the 3d is less than 4s, but again, we have to be careful about making these statements because they are overly simplistic, as I've said several times now, and so I hope you understand that being the case. We have these nice little rules from the Aufbau principle, but they do oversimplify the real situation. So this ends our wonderful discussion of the Hartree-Fock principle and orbital energies. In our next video, we'll start to talk about molecules. I bet you thought we'd never get there, but it's coming, so we're looking forward to it. See you later.